addition of the codes, but still they can be used if you are making new code. But for the existing codes, commercial codes like a Fluent, OpenFOAM, these all codes will be used only for to learning purpose. Okay, so you can use your software Fluent, but now everybody uses them in a different way. So if you use them properly, you should be able to actually get those results with a high precision. So that's why now these cases are used to teach the new person who's entering the CFD community and using the already well-established CFD course. So I think I'm clear about the what is the use of these test cases nowadays. Okay, so the slides I will share you in the email. Okay, I will send you the email, and what you will see here is that this case was developed on the uh, ICM CFD and the Fluent, and it is a published course on the Udemy. But what is different here is that I'm going to like solve this case in a like a most simplest possible way, and definitely this is going to be live course, so you can ask me questions as well. So there are few things that will be like a slightly different, which I will talking in the class and also on the slides. So here is the course contents and also discuss about the ICM CFD and the Workbench. And these are my main references for this case. This is the Armeli BF. This person is not no more in the world. So he was the first one who actually investigated the this case experimentally and theoretically. And it was published in Journal of Fluid Mechanics 1983. And then afterwards, what happened is that the Biswas, he took the same case, but then he ran the case for different expansion ratios. I will explain what is expansion ratio. And he published the paper in the 2004. And mostly his work is on the CFD. Okay. So the experimental work was done earlier, and then the CFD work followed that work. But this is also very old work, like 20 years ago, this work even. So this is the picture from the Biswas paper. So here you see that this is the this part is the inlet, and you can see here one thing that what they did is that they applied the velocity profile. So you might ask a question, why velocity profile? Because if you this is a parabolic velocity profile. So when in a case of, let's say, simple pipe, if you take a pipe, the pipe will inside the pipe, it will take some time to establish the flow that we call the fully developed flow. So that is like a entrance length. Okay, once entrance length is completed, then the flow will be fully developed, and you will see the velocity profile as a parabolic. Okay, and the definition is that for the fully developed flow, which is this point onwards, the definition is that the velocity will not change with the x direction. Okay. But the problem is that if you the if you increase the Reynolds number, the formula is very simple in the laminar pipe flow. You can check it the Munson's book or the Fenneman White book, that the L by D is equal to 0.05 into RED. RED means Reynolds number based on diameter. In this case, we take the hydraulic diameter. In circular cases, this will be simple diameter. So now simply see that if this is equal to the let's say this step height is equal to 1. Okay, so diameter in this case would be equal to 1. And but for the rectangular channels, the hydraulic diameter actually is equal to the 2h, because 2D case, the parameter would be the, like, we will go upward 1 point, then again we go back. Okay, and we use the formula 4a upon p. So if you put the values for a, area will be the like height into the third dimension, which is equal to the 1 units. So eventually you will get the two quantities here. So this will be like L by 2h is equal to 0.05 RED. So if the h is 1, so this will be 2. So L is equal to 0.05 into 2. And the Reynolds number is, for this case, we are going to take is the 100. So let's take the 100. So the entrance length, this is the entrance length, not the actual length that we are modeling here. This is the entrance length. and this is equal to, now this will be the point 0.01 into 100 is equal to 10. It means that we have to enter the 10 meters extra here. Now this will make the domain size larger, and this will result in the like a large computational time, especially when the case is transient. So that's why, to avoid that thing, what we do is that we apply the that developed velocity profile on the inlet. That we can do with the help of the UDF. Okay, the UDF is the short form for the user defined function, and this is the C code that add the extra functionality in the Fluent or any other software. Okay, so directly we don't have the any option for the applying the velocity profile. So the Fluent gives you, now also they have the like expression function, and also tabular data you can also apply. And if this is a simple case, you can even apply the simple table of the velocities. You can take it equation into the Excel, get the points for the x and y, and so you can apply that directly through the simple text file. Okay, but that we're not going to discuss. We're going to discuss with the UDF. Okay, so just give me. Okay, I think I should be like doing it this way. Okay. So if you go through the paper, I have given on the WhatsApp group. So these two papers are given. So go through this paper. First reference, Biswas paper. So they will tell you that the for Reynolds number greater than 400, the flow becomes three dimensional. So it means that the you cannot solve this case as the a two dimensional. And secondly, three dimensional means that it will have the turbulence. So to make the flow analysis simple for learning purpose, what I did is that I kept the Reynolds number less than 400. So I took the a safe value of the 100, and I used the expansion ratio of 1.9423. Okay, expansion ratio is basically is the ratio of the total channel height, which is the here, and divided by the inlet channel height, which is before the step. Step is here. Okay. So this is equal to the 1.9423. So you can change the values like a 1.5 to 3 like that. But I have taken the value of 1.9423. And for this expansion ratio, this is not number, the real-time length. After this step, because there is a sudden separation point here, okay? There's nothing is there, so flow is separate from this point. And depending on Reynolds number means the velocity, definitely. So higher the velocity, the flow will be going further downstream, okay? With a more pressure, more velocity, pressure flow will go for the downstream. So based on the Reynolds number, you can judge that thing. That flow will be like maybe attached some point here, okay, depending on the Reynolds number. And this XL, the real-time length will be different, okay. So our task is there to find out the this real-time length after the step. So this is equal to for these cases in the Biswas paper and also the original reference paper 2.70584 meters. So our CFD should be able to actually predict these values as well. Okay. So now if you analyze these things, so Reynolds number is based on diameter. So this is equal to the buck velocity, that is like every velocity because we are applying the velocity profile, and the hydraulic diameter, and that is equal to h. For this case, because this will be going up and going by x, this will be equal to twice of the this height. So this is a 2h, the small h, small 2h, and divided with viscosity. So now how this can be done? So we know about this value that the Reynolds number is equal to 100. Okay. Secondly, what we are doing is that we know that the expansion ratio h by h is equal to 1.9423. Okay. So here what I'm going to use is that I'm going to make it very simple, and I will just take the h is equal to 1 meter. So this will make the things very simple. So this means that the now h will be equal to 1.9423. Now if the h becomes the 1.9423 and but h is equal to small h plus s, it means that because the h is equal to 1 meter, so the s will be equal to the 1.9423 minus 1 is equal to 0.9423. So step height would be equal to 0.9423. This is how actually we find out the unknown quantities from the few given properties like the Reynolds number, expansion ratio. We're given only two these things. So from these two values and the picture here, actually I got the values for the this geometry. Okay. And also the same paper, they say upper stream length is equal to the 5h. So 5h will be equal to 5 into 1 is equal to 5 meters. Downstream length is equal to 10h. So it's equal to 10 into 1 is equal to 10 meters. So you can also increase these lengths and you can see what happens or what effect they will make on the results. If no, then you can use these values. Okay. So maybe you can reduce the values and see what happens with with the results. Okay, so you can check that thing. This is called a sensitivity analysis, and you can see that how much effect will be there and after which value effect will be not there. So you have to like take the minimum value where the effect will be not there. Okay, they will not be affecting results on the interior of the your flow problem. Okay, so now I have gotten the value of dh because h is 1, so dh is equal to twice. Okay. And now for a Reynolds number based on diameter, this is equal to the this formula. So rho, this is the bulk velocity, and dh divided by mu. This bulk velocity actually is the average velocity of the flow. So for this case, we are taking the velocity is equal to 1 meter per second to make the things again very simple. But this will not make any difference because if you are simulating same Reynolds number and same expansion ratio, basically you are solving the same case. Yeah, you should be able to get the similar results. Okay. So I can now solve I can take the density as 1,000 kilogram per meter cube. That is density of water. Okay, COD we don't need to be having the some fluid. It can be any fluid. Only thing is that it should be satisfying Reynolds number and other condition like the expansion ratio. So now I have the this value dh is 2 meters. My velocity is 1 meter per second. Okay, density is equal to 1,000 kilogram per meter cube, and the Reynolds number is the 100. So I can now solve for the viscosity. So viscosity becomes its value becomes the Reynolds number, the rho ub dh divided by the Reynolds number. So put these values 1,000 into 1 into 2 divided by 100. So what we get is that we get a Reynolds number, the viscosity as the 20 Pascal second. And also this is units are also kilogram per meter second. Okay. So now I think that you know that how we got these values. So what we have now we have the geometry. Okay, we have the geometry and as well as the fluid properties and the flow properties. So what we have right now that we have the UB is equal to 1 meter per second. It's a flow property. We have the fluid properties like a density is equal to 1,000 kilogram per meter cube and viscosity as 20 Pascal second or kilogram per meter second. We have geometry properties, so H is equal to 1, S is equal to 0.9423. We have this upper stream length LU is equal to 5 meters and we have the LD is equal to 10 meters. Also, we have this total height on this part that is equal to the capital H is equal to 1.9423. So now we have everything to solve the problem. Okay, so we have everything to solve this problem. So now let's go further. Okay, so to apply the velocity profile in the laminar flow in the channel, the velocity profile is parabolic. In the pipe flows, the maximum velocity is equal to the twice your average velocity or the mean velocity. Okay, that is this velocity. That is average of these all velocities. Okay, but for the channel case, the velocity you can read some good full mechanics books. So the u maximum actually is equal to the 1 point times of the u average or u mean. Okay, so we use this value. Now this is the pipe case, and this is a three-dimensional thing. This is a channel flow. Channel flow will always be the two-dimensional. Okay. The only thing is that the same velocity profile will be copied on the different z locations or the third location. So for pipe flow, this is very simple to apply. But for channel flow, the channel can be at any different height. Okay. So the profile that I have gotten from the book is that it's a 6 times the U mean, while the U maximum is a 3.2 UB, that is a 1.5. Okay. So this is the formula is ux as a function of x, uh, because that is like we can plot along the this axis. Okay. Now this can be written as a maybe the uy. Okay. Uy actually, so this should be uy. 6 you mean y upon h. So h is the height. So height from the half. Okay, here and here. But what we are going to do is that we are taking the height directly from the here, from here to here. Okay. So y by h and minus y by h whole square. So, but the our bottom is not actually at the zero, but we have taken the our step at some different height. So now we have to introduce the so our y zero is equal to here. So what we did is that the step is somewhere. This is the y minimum. This y minimum actually is equal to the 0.9423, that is step height s. So we introduce the formula y minus y minimum divided by h minus the same formula but y minimum whole square. And so we are going to now put the y minimum is equal to 0.94, y maximum 1.9423, y not is equal to 1. Okay, so this is UDF, and this is actually is adjusting that thing here. So what we defined is that we defined the U maximum is equal to 6 times the U minimum. So this is only to simplify the problem. Otherwise, the U maximum is equal to 1.5 into the U mean. So actually there is another term that is the 4 there in the equation. So that 4 into 1.5 will be equal to how much? Is equal to 6. There is actually if you can write down this one as a u 4 into u maximum. Okay, so instead of making the things complicated, what I did is that in terms of programming, what I did is that I just simply put the my u maximum is equal to 6 times the u mean. Okay, so u mean is equal to 1 meter per second, and here defined the y minimum is a 0.9423, y maximum is equal to 1.9423, u mean is like 1.0. This is the command for the C for the Fluent. So define profile, velocity profile T, and the I. These are the arrays. These are the variables, and this is the phase on which I'm going to apply. That is going to be the inlet phase. So you can apply on any phase. If you attach to any phase, that will be that phase. Okay. So and h is equal to y maximum minus y minimum. So here what we did is that instead of 2h, actually we converted this into the single h. Okay. So this is the formula. We just put the formula here. This is the y maximum, u maximum, that is the 6 times the u mean. So this will be the 6 u mean, and the y minus y minimum divided by h minus y minimum, y minus y minimum divided by h whole square. So to write down the square, we actually multiply these two things twice. Okay, so multiply this with this will be the square. So this is the problem that we are going to solve. Okay, any questions? Any questions?
No, sir.
Okay. Okay, so now I'm going to actually open the new workbench session here. So type the first letters, few letters for the workbench. The workbench was 24 release 2. And the one more thing is that I'm going to take my geometry, this side on the negative x-axis. This point will be on the 0 y. Okay, 0 y. But x will be on the like this. This will be them on the 0 0. This point, this location. So just keep this thing in mind that this will be at the this point location will be at the y0 x0. Okay. Okay, so here I'm going to use the Fluent and the Ansys meshing. So I will directly use the Fluent. Okay, I can make my own system like copying the components like geometry, and then I can like drop the mesh on the that one. That will be same thing like a geometry now mesh we have. Similarly, I can drop the Fluent on the mesh, and then the results. Okay, results actually is for the CFD post. We are not going to use that one. Fluent is a Fluent. Geometry is done in the design modeler. Meshing is done in the workbench meshing or SS meshing. And we can post-process the results in the CFD post, but we're not going to do that thing, okay? So I'm going to delete these all things and we work on the case here. So select them all and press the delete key from the keyboard, like any Windows command. Okay, and save your project file. I will be putting it in the my working folder that I'm going to share with you also. This is the file I'm going to share with you. And I'm going to share you file in the zip format. Okay, there is a uh, zip format you have already seen in the Windows, but there's a zip format for the ANSYS file, and that is provided by the ANSYS itself in the file menu here. So I will use that zip format. Okay, so I'm going to like backward facing step. Okay, double click on the geometry. So this step height is equal to the 0.9423. Just keep this thing in mind, okay? So XY plane, keep click on the look at and go to the sketching. Any questions so far? No? Okay. So this is the XY plane. So I'm going to draw the lines and also make sure that the scale here, this should representing the our geometry. So like 20 meters would be okay. Okay. Or maybe you can make it 10. Okay, now I'm going to draw the one line on the just on the x-axis. Okay, one line vertically, then one line backward side, and make sure that whenever you apply on the any point, this P symbol should be there. So how you can turn on that symbol if not appearing on in your design model? You can go to constraints and auto constraints and turn on the global and cursor both at the same time. Okay, draw line and P symbol should be there. Okay. And now I will drop it vertically. Okay, so now I want to remove this extra geometry here. So I will go to the modify and there's an option for the corner. So I will select the two outside lines and they will remove the corner automatically. So we get the our required geometry. Okay, so if you like hide the plane and the sketches from here, you will see the geometry in this way. Okay. So just display the plane here and now we are going to get the dimensions. So I put the dimension for this, the step, the downstream length, upstream length, and I want to also move the step height on the inside and this one close to my geometry. So you can use the move command. Use your left mouse button. Just hold the your dimension and drag your mouse. Okay, simply, very simple. Okay, so and so we have the now step height and also the edge, small edge, which is here. Or you can directly give the total height. It's your choice. Okay. So I'm going to give the total height, which is here. So this is equal to 20 meters. And this one is sorry, this is the 10 meters. And this one is a 5 meters. The step height is 0.9423. Just confirm that thing. Okay. Total height is a 1.9423. Okay, again, I want to move my dimensions close to geometry, so just hold and move it like this. So just make sure that the step height is the 0.9423. Okay. 0.9423. 0.9423. Total height is the 1.9423. Okay. So everything is all right. So now I will go to modeling tab. Now our sketch is done, so you can hide the planes from here and you can display the sketch here. Okay. So what I'm going to do is that I am going to actually now change my can you see the screen? Can you see my screen?
Yes, sir.
Okay. So now constant menu,
Yes,
and I'm going to use the surface from sketches. Okay. Right. And this is the like only lines, and these are sketches. So the sketches cannot be, we cannot make the mesh on the sketches. So we need to have the body. So bodies can be two types, three types actually. Surface bodies, the volume bodies, and the third one is the line bodies. So for FEA, line bodies can be used also for the line members, but for CFD purpose, only surface bodies for 2D cases and the 3D bodies for the 3D cases. So we are going to make the surfaces here from sketches, and a sketch that I'm going to convert to sketch to the surfaces is this sketch number one. So select the sketch one and click on generate. So now we have the surface here. Okay, now we have surface here. And now, but to get the hexa meshing, a structure meshing, actually, we need to divide this geometry into three parts so that I can create the hexa meshing. For hexa meshing, we need to have the four sides. Okay. So if I divide by this way and this way, what will happen is that now this geometry will have the four sides, 1, 2, 3, 4, 1, 2, 3, 4, and the 1, 4, 3, 4. So I'm going to make new sketch actually to divide the geometry into three parts, 1, 2, and 3. So I'm going to go to XY plane, same plane where I made my original sketch. First sketch is done automatically by the design modeler. For second sketch, you have to give the command explicitly. So you have to like click on the new sketch here, select a new sketch, and just draw the two lines. So one line vertically, second line horizontally. So it will divide into the three parts. Okay. So go to modeling tab, choose the sketch number two, and now go to constant menu. And now we have to make the lines from the sketches. Okay. So, and also make them add frozen. Add frozen means that this will not be merged with the existing geometry here. Although they will not be merged, they are lines, but in case of the surfaces, they can be merged. Okay, so I want to keep them separate bodies, separate entities. So I want to add them as the add frozen. So add frozen means that they will not be merged, even they are the same location. Okay, so click on generate. So now we have these two lines with us. Okay, these two lines. Okay, so I will use these two lines and I will subtrate my surface into three parts. So I will go to the tools menu and face split here, choose a face and choose the line option from the selection filter and choose these two lines. Apply and then click on generate. Okay. Now the line bodies have done their task and you can now suppress them. We don't need them. And you can see that now we have three surfaces, three faces. Okay. Clear? The last thing is that in the geometry part is that we have to provide the name selections that will be used for the boundary conditions where we can specify the boundary conditions actually. So to define the boundary conditions, we must define the name first in the design modeler. So select this boundary and right click here, name selection, and this will be the our inlet from where the flow will is going to be go inside the my domain or our domain. Okay. This is going to be the these two. So to select two edges, you have to like click on the control key so that you can select that multiple entities. Again, right click here, name selection. This is going to be the outlet. And every time when you want to like complete the command, every time in the design model, you have to click on generate. Okay. This is my step. So I'm going to right click here, and this is my wall and wall of the what step. So wall for the step. This is my downstream wall. So I'm going to right click here, name selection, and the wall, and this is the downstream. So you can write down the DS downstream. Okay. And this one is the my upstream wall. So I'm going to put the wall and the upstream. Generate. This is going to be the top wall. And generate. Okay, so now you have to save the project file at the same time. So now geometry is done. We have also done the name selections, and also we make sure that we have the our point for the like here is exactly on the 0, 0. So select the tools menu, analysis tools, and the entity information. Okay, and select the vertex here and click on the corner. You can see the coordinates are the 0, 0, 0. Okay. Okay. So let's now. Okay, one more thing is that the geometry is two-dimensional. So that's why we made the geometry in the XY plane. This is a requirement for the Fluent, okay? If you're solving case 2D, then your geometry should be in the XY plane. So just click on the this here and click on the view menu and the properties, okay? Now click on geometry and make sure geometry analysis type here is 2D, okay? Now double click on the mesh. And here we are going to create the structure mesh. So what I did is that actually I provided you the one mesh. Uh, one mesh is given in the forum here. So this is done in the ICM CFD. Okay. So that mesh you can also use. This is very good quality mesh actually, and the same mesh which is shown in the workshop here. Okay, this mesh. So I can provide you the two meshes, the mesh one and mesh two. Mesh one is a slightly coarser, mesh two is slightly finer. So you can see the difference is 0.2%, and in the fine mesh, this is the 0.01%. Okay. So now to make the hexa meshing or structure meshing in the workbench meshing is very simple. First thing is that you have to click on the face sizing, face meshing. So select these three faces. So this is making sure that you are going to get the collilators. Okay, collilators are requirement for the structural meshing, definitely. So first thing is that you have to select them. Okay, although this may not be required in many times, but sometimes this may make the issues. In that case, this will force them to make the structure mesh. Okay. Now after that, I'm going to click on the sizing. Select the edges first and then the sizing. Okay. So I will select these three lines which are the parallel to each other. And here I'm going to put my number of divisions or number of cells. So let's put 30 divisions here. So this is what I thought are enough. Okay. But I need the finer mesh towards the wall here because the flow will separate from this point. So we need the finer mesh here, not on the upper side. So I just need a fine mesh over here. So I will use the biasing. So I will use the biasing for the only one side. And biasing factor of 30, this is enough, I think. Okay, then I'm going to use the edge sizing on these three edges. And number of cells here I'm going to define will be around 80 because the flow separation will occur here and the flow circulation will be happening here and then flow will reattach here. This should be very fine mesh actually, at least in this region. So again, I will use the biasing, one-sided biasing, and factor I'm going to use maybe the 40. So the factor is like a variable that you can change it from 0 to like a 10,000, sometimes 50,000, also sometimes 2 legs to get the required mesh. Okay. So I think this is okay. This is also okay. But once we get the mesh done, we can like we can modify them and we can recreate the mesh so that we can have the required refinement in the corners over here. Okay. So we are done with the mesh here and we are done with the mesh here. So now we are going to create the mesh on step. Okay, here I'm going to use more cells here, maybe like 50 cells. And I will make the mesh refined on the both sides, top and bottom, like this. And let's make it 50 cells and let's make the bias factor as maybe a 50. Okay. So let's create the mesh. So click on generate and see which side we didn't specify. This also will be very much clear after making the mesh. So we have done the meshing here also, and here, but we didn't define the mesh here. That's why it's creating problem here. Yes, please go on. Ask a question.
Sir, what is the difference between this factor and the growth rate?
Please.
What is the difference between this factor and the growth rate? Can you hear me?
Yes, the growth rate actually is the growing from the like a first is the one size is the one. So growth rate means 1.2 means that it will grow them by the rate of the 1.2 times of the first size. Okay, but this is
Okay.
same thing. Like I cannot give you right now formula. I will discuss that in the WhatsApp group, but it's almost similar thing. But only thing is that the now the bias factor is like having the any value. But this growth rate is having value like from like a 1 to the maybe 1.58 maximum. Okay.
Okay, sir. Okay, sir. Thank you.
Okay. So here we have the okay, the sizing for the edges. Okay. Sorry. Okay. Let's make it like a 40. And I will use the biasing factor again on the one side. Let's make it like a 30. Okay, now you can see one thing that on the top side, the biasing is applied on the other side. Okay, why this happens? Because the edge direction actually plays a role. So this edge may be direction having on this side, but this has a direction on the opposite side. So the biasing applied on the other side. So we have the solution here. There's a reverse biasing. So select the reverse biasing and select the edge here. Simply apply, and this will reverse the biasing on the two sides. Okay. So now we have the sizing here, here, here. I also make sure that the here the biasing was applied properly. Okay, this should be on the same side. Okay, this is clear. This one also okay. This one is also okay, and this one also okay. So now you can go for the mesh generation. Okay. Now zoom the area, and what you see here, we see that the mesh on this side. Okay, you can see here this thing. What we are trying to do is that the mesh on the corner should have the same size on the both sides. So this mesh should be like this way. Clear? So it means that now we have to change the biasing here so that the cells can come close to the corner here. Similarly, here as well. So the biasing on the bottom side is okay. Here is okay. But here and here, this is not okay. Here and here. Okay. So now I will play with biasing here. Okay. So this biasing should be increased to the maybe like a 50. Okay, or maybe 60. And similarly, this side maybe you can make it 60 here and generate. Okay, it seems like okay. There is a one thing that actually now we can force because we applied the biasing very properly. So one thing that can be like helpful now is that we can actually here we can force the biasing here. So there's option that capture curvature no. So make it no, and here is the 1 minute. Here is the behavior is soft, so make it hard. Okay, hard means that the soft is it will be decided by the software that what they are going to apply. So maybe they will consider your sizing, your growth rate, biasing, whatever it is, but they will apply the growth, the biasing, which is actually will give you the best mesh. So it is like a decided by the software. But if you make it hard, then it will apply whatever you are trying to do. Okay, so this is between difference between soft and the hard. So you can see now the biasing has now working here properly. So now I can change the biasing to maybe 80 and click on generate. So now this is almost equal. So now let's work on the this side and this side. Okay. So on the this side, so let's make it like 100 and also make it like a hard. Okay. So I'm going to make the behavior as a hard here and generate. Still not, so I will go back and I will maybe specify the biasing factor as a 200. Now this is almost close, okay? Almost close. So now let's work on the biasing here, this one. So let's make it like a 100 and make it hard behavior. And now let's check the mesh. So this is okay here, but here we need to define maybe the biasing factor of maybe 150. This is all right, okay? So this is the mesh we got after the all refinements. Okay, so you can see the statistics here. So number of cells here are around 7,800. Okay. Any questions? Any questions? No?
No, sir.
Okay, last step is that we have to update. So update actually means that uh, the this will actually update is like we can directly say the generate mesh should also do the update the mesh also, but the update has a specific functions here. Number one is that it will check that there is some overlapping between the name selection or not. So now one name boundary condition name cannot have the two surfaces. Inlet has this surface, and now inlet cannot have this surface, which is a part of the step side step boundary condition name. Okay, so sometimes this happens that by mistake we put the same surface or same edge into the two boundary condition names. So this will check them over here. Number two is that it will check for any errors. Okay. Third is that it will export the mesh for the Fluent actually. So right now we generated the mesh, but the upgrade will check the any errors. It will check the any problem in the name selections, and then it will export the mesh in the Fluent format, that is .msh. So we have to click here on the update. You can see the mesh translation was to Fluent was successful. This if this message is there, then everything is all right. Okay. And last thing that again you have to do is that you have to save your project file after the every operation. Okay. Now double click on setup and open it. You can see now we have the only 2D option is here, and this is also grid. So you cannot change it. Okay, so this is done because we change the geometry in the geometry analysis type to the 2D. Okay, so now because this mesh is very like a simple mesh, very small number of cells, so we can run double precision. And the only thing is that double precision will actually increase our memory from for single precision 32 bits, double precision is 64 bits, so memory requirement will be double with double precision. So if you have enough memory, you can use the double precision to have the more accuracy. Okay, and number of cores in my computer are 4, so I can use a maximum 4. Or 2 will be enough also for this case, or maybe 1 is enough for this case. Okay, click on start. But number of cores should be in the power of 2. 2 power 0, 1. 2 power 2 is the 4. 2 power 1 is the 2. 2 power 3 is the 8. So you should always select the number of CPUs cores as the 2 power n. So 2 power 0, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 102, like that. Okay. Okay. So you can see the mesh here. You can click on display and select the both edges and faces. They will show you the black color lines like this. Okay, if you select the both edges and faces in the 2D case, this will show you the mesh and the black lines. Okay, so now you can zoom the area and you can see the on the step the mesh looks like in this way. And you can change the colors also by surfaces. So the boundary conditions in this case will have the now different colors. Okay, so if you hide the interiors and uncheck the faces. You can see now they are in the different colors. So all the boundary conditions, they are the different names, different numbers, and different colors now. Okay. And if you display the surface bodies and interior bodies, you will see the mesh here. Okay, so and click on report quality. So minimum maximum quality is a 1. So 1 is the best, 0 is the worst, and minimum for the Fluent is the 0.01. So right now it's a 1, 1 is the best. Okay. And aspect ratio is like a 450. It should be less than 1000 for single precision. It should be less than 10,000 for double precision. And in the boundary layer, the mesh can go up to like a 1000 for single precision. But for the away from the boundary layer, the mesh should not be exceeding like a 100. So here maybe we have the very highest aspect ratio, but it's not a problem right now. Okay. Okay. So now what we are going to do is that we are going to like select the model. This is the laminar flow. So from viscous, I'm going to change the turbulence model to the laminar flow. Number one. Just steady state, yes. No transient, planar flow, yes, planar flow. No gravity is there. Second thing is the material properties. So we actually provided our customized material properties to match the Reynolds number. So double click here, and values we provided for the density was the 1000, and we calculated viscosity as a 20 kilogram per meter second or Pascal second. Simply click on change create. Okay. And now double click on the boundary conditions. Make sure that our boundary conditions at the outlet, the pressure should be equal to the zero gauge pressure. And the atmospheric pressure should be equal to the operating pressure, which is 101325. So this means that now our absolute pressure at the outlet is actually 101325. Okay. So without any external source, any external power, the gauge pressure will be zero. In the inlet, we define the velocity profile with the help of the UDF. So UDF is actually is given here. So okay, so this UDF actually we are going to read into our Fluent. Okay, so we are going to apply this velocity profile, parabolic velocity profile on the inlet. Okay, so we apply this UDF. So and that to apply UDF, we have the on the bottom side the parameters and customization. From here, we have the user defined function UDF. Okay, right click here and click on compile. So we are going to use a compiled UDF, and make sure that the UDF that I'm going to provide you, it should be in the same folder as this folder here. Where this folder is here, this is the backward facing step file name. Main folder will be this one. And then if you go to the setup, you can see the our directory name is the triple F. Okay, triple F. So you should go there. Okay. So I'm going there. I'm going there. This is the training folder. This is the our course folder, which is here and here. Backward facing step is the only like a single file that is going used for the management, but its files are saved in the its working folder, which is the same name underscore files. So DP0, triple F, Fluent. So what we have to do is that we have to make sure that their UDF should be inside the same folder. So I'm going to copy the UDF actually from the my old file which I solved today in the early in the morning. Okay, so same UDF we're going to use here. So right click here, copy. So back and here. Okay, so paste the file here. So this is must. The UDF should be the same folder where our Fluent file is. Okay. Okay, so now add. Sorry. So double click on the velocity profile and click on OK. Okay, one more thing is that to compile the UDF, actually, I installed the Visual Studio, downloaded from the Microsoft, and I actually it was, I think the crack was I got from the internet, but you can also use the built-in compiler. If you don't have the that Visual Studio, then you can use the built-in compiler. Okay, but I'm going to use the directly because I already installed my Visual Studio, so I can build it. So after building, and you, if you don't see any error or warning here, then you can go and load the file into the Fluent database. Okay, and now I will go to boundary conditions and double click on the inlet. And in the velocity, I'm going to click on the arrow drop down boxes and I will choose the velocity profile UDF. Okay, apply and close. Then I will go to monitors because for laminar flow, the convergence can be like the convergence criteria, like it can go down to the very low values. So that's why I'm going to put the very low values here. So you can put the some zeros here. Click on OK. Now you can change the into the 1 e power minus 15. So let's change it to the 1 e power minus 20. Okay. So you can copy this one, this value, and you can paste them into the remaining two boxes here for the x velocity and y velocity. These are the actually momentum equations. And this is our mass conservation continuity equation. These are two momentum equations. Apply. And I will initialize with the help of the from the inlet. Click on initialize. Go to run calculation. I will put the 500 iterations, but I think that this will be converged within the 200 iterations. But because we have put the very low values for residuals, this will not show you any message. And that's the point actually. If we get the convergence 10 power minus 3, so this show you the message, but that convergence is not happened. Okay, so don't go about the message here on the Fluent text box that it gives the option. This gives you the message that the solution is converged. This is not a convergence actually. Solutions converge when our result plots are now no more changing. Okay, you can see on the screen if they are going down, and after certain time they will be the straight line. The result values can be for laminar flow. I think 10 power minus 6 or less than that one is enough.
Except for turbulent flow?
No, it's a laminar flow right now because in the
Okay.
starting we discuss about this thing that for Reynolds number less than 400, the flow is confirmed to be the laminar flow. But after 800 Reynolds number, the flow is completely turbulent. In between 400 and 800 Reynolds number, the flow is transitional. So we chose the safe side and we choose the Reynolds number is equal to 100.
Thank you, sir.
Okay. If the mesh is okay, then you should get the very good convergence actually. Okay, meanwhile solution is converging. Let's discuss the few things here, okay, for solution. Number one thing is that I can encourage you that you can go for the different expansion ratios, okay, for different Reynolds numbers and different expansion ratios given in the BISWAS, okay, number one thing. And number two thing is that that's important thing, that if you want to observe the separation and the rearrangement of the flow, so how that can be observed? See, whenever flow is going to be separated, so what will happen is that in terms of boundary layer, what will happen is that before the separation, before separation, just give me 1 minute. Okay. So okay, Fluent takes some time in the workbench mode. Okay. So I'm just waiting for the processor to be freed. Okay. Okay. Okay, now if you go to monitor the radius zeros, you can actually have the proper view of the this result plot. So you can simply click on plot. This will fit into the window. Okay, so our like continuity converge to 10 power minus 14. Momentum equation they converge to 10 power minus 17 and minus 18. Okay. Okay, so if you take a look on the definition of the separation, you can see this is the in terms of the wall shear stress or the shear stress. Okay. So in terms of wall shear stress, you can see that the shear stress, once the flow is attached here, you can see the velocity is positive. Okay. And as you go, like flow is starting to separate. That's not separated, it's starting to separate. You see that the shear stress value will be reduced. Okay. Will be reduced and slope will be very, very high. And here then on this point when separation like reverse flow is there, separation bubble is there, in that case the shear stress will have the negative value. So its magnitude will have the positive values. It cannot be possible to have the magnitude negative, but the x shear stress will give you the negative value. Okay. Wherever flow is separated, it will show you negative value. And when the flow separated or reattached, separation or reattachment point, they will show you the value as a 0. So 0 means that this is the separation point or the reattachment point. Okay. And negative value means that we have the reverse flow there. Okay. Separated flow there. And positive value means that the flow is attached. Okay. So we use this fact, this technical fact here. And I'm going to also I'm going to save the project first. Okay, sorry. Everything's okay now? Okay, let me repeat. Okay, let me repeat. Okay, so let me repeat. So I was telling you that if the separation is there, so what will happen is that the for attached flow, the boundary will be showing you the behavior like this, okay, and the wall shear stress having the positive slope, okay, slope like that. As separation is occurring, like a flow is going to the very weak boundary layer, you will see that the wall shear stress will start to have the more slope, okay, more and more slope here. Then when separation occurs, the negative slope will be there, okay. So that is only possible when we are actually getting that both magnitude and direction. So for the the velocity, the shear stress at the wall magnitude, you will only see the negative, the positive value, zero values. But in case of the X shear stress, you can see the negative values also. So the negative values shows the reverse flow, and the zero values means that the either flow is separating from this point or flow is reattaching there. So these locations, zero shear stress, X shear stress, will show you that they are either separating from this point or they are reattaching. Okay, and once after that, after reattaching, the shear stress will again get the positive value. So it means that now flows attach fully. So we have to find out the where the value of zero shear stress is there. Okay. So for that, what I did is that I went to the Fluent and I click on the XY plot, and I chose my wall fluxes, and I chose my bottom wall, which is the downstream. Okay. Downstream wall, and click on to save and plot. Okay. It should be the X shear stress. Okay, so here you can see that the first zero value, this zero value means that the separation occurred here. Okay, then the negative shear stress occurring means the reverse flow is there, and then finally we have the attachment point is around 2.6 or 2.7. Okay, to just give you idea about this flow, I plotted the same picture in the tech plot. You can see this is reverse flow is happening here on this corner. So this is separation point actually. I'm not plotting on the upper line, otherwise the separation point will be on the second side of the line, which is up to here. But you can see the reverse flow here. But the flow attaches here. Where attaches here, it cannot be clearly we can see from the just these lines, but it looks like that the flows attaching may be somewhere here. Okay. So let's display the axis. So x-axis and the y-axis. So the attachment is maybe occurring at the something like here. So this is like a complete geometry five also there. Subtracted, you can see this is around maybe a 2.7, 2.6, between 2.6 and 2.7. Okay. So to get it value, exact value, we have to use the Excel. So I'm going to write the file. So write this file. This is the X shear stress. Okay. Open the Excel file and go to the data and click on the file from text file, and click on the all files. Okay. So this is actually is over here. This folder dp0 triple f fluent, and this file is here x shear stress. Okay. Click on import, next, and finish. Okay. Copy this data and plot this data over here. Okay. You can delete these columns and also these two rows. Okay, so what we have here, this is the x location along the line. This is the x shear stress. But only thing is that it's not starting from zero. Okay, zero is somewhere in the middle. So we first we have to rearrange the data. So select these two columns and click on the sort. So based on the a column and from smallest to largest values. So now it's starting from the 0 to the 10. Okay, so now just go and see where the shear stress is changing direction from negative to the positive. Okay, so I'm going there. So it is changing the location here. Here. Okay. Okay, so now I'm going to use actually I need the value of the x where the shear stress is 0. So I'm going to use the online interpolation calculator. Only thing is that the trick is that this trick is very important. That which one is going to be x and which one is going to be the y. So x is anything where we have the known the all three values. Okay, so this is I need the value where the shear stress is 0. Okay, so I know these two values. This is like a x1, this is a x2, and 0 will be the my x. And this one is going to be my y. This is the y2, and this is going to be the corresponding value of the y is the y. So any known values are the x, and unknown values will be the y. So in the x you have to put the these two values and the x. Okay. So here. So put the value as a minus 2.77158, 2.37478. And what we need the zero shear stress. Okay, so zero. So Y locations are the 2.58024 and 2.76249, and click on calculate. So this value is a 2.67. Value is now 2.67. This value. Okay, what is actual value? Actual value is 2 point something 705. Okay, the actual value from experimental data is equal to 2.705. This is the value here. Okay, and the value we are getting is this one. Okay, so how much difference is that there? So calculator and put the 2.678391 minus 2.70584 divided by the original value 2.770584 multiply with 100. So error is a 1%. Error is a 1%. So if you uh, let's do it again. 2.67839 minus 2.70584 divided by 2.70584 into 100. So it's an error is a 1%. Okay. So if you increase the mesh quality and not the quality is one already one, but if you increase number of cells here in the impound region, actually you can be very close to 2.70584. Okay. Any questions? Any questions?
No, sir.
So how was the today's class? What was helpful?
It is good, sir.
Yes, sir, it's helpful.
Okay,
Yes,
so I
sir.
will
Good.
share you the PPT file through the email. I will share you this file also, but I'm going to share the file in this format. Like I will go first. I save the file here. Okay, so you should be very much carefully see this thing, how files are shared. So I'm going to click on the archive. Okay, from file menu archive. This will be single file now. Okay, this will be single file, and extension would be the see here. So instead of the extension of WBPJ means workbench project file, it will have the WBPZ, only a Z here. Okay. So this file you have to share with me, or I will share with you. So how to open that file is a very simple. So let's say I close the file. Okay. Double click on this file or directly open the workbench is also possible. So if you open the workbench, then you have to click on the, like if you open directly workbench, then what you have to do is that, so there's a two-step here. First, you open the file and then save the file with a simple file format WBPJ, or you directly open your workbench and save the file, the some name, and then unarchive the file. Okay, these two methods are available. So Okay, so this is double clicking on the WPPZ file, WJ Workbench, WBPJ PZ. Okay, so then I have to save the file with some name, and then I can use the file. Okay, clear? Okay, so see you tomorrow, and tomorrow we are going to be doing simulation on the supersonic flow on the symmetric arrow file. Okay. Okay. See you tomorrow. Thank you. Bye bye.
Okay, sir.
Thank you, sir.
Thank you.
Bye, sir.
Thank
Thank
you,
you.
sir.